Let's begin by defining the mathematical problem associated with solving a first order differential equation. We are given a first order ODE in this form: dy dt equals f of y comma t. This right hand side depends just on the dependent variable y and the independent variable t. And we are also given an initial condition on the dependent variable y at t equals t0 is a given value y0. This is a constant number that is known. And what we want to know is the solution y as a function of time, how this evolves. That is the object of what we are trying to do. And more broadly, we want to understand how the solution depends also on the initial condition. So when we write it in this form, we are expressing not only the dependence of y on t, but how this dependence is also influenced by the choice of the initial condition. So we are looking at a collection of solutions with y0, the initial condition, as a parameter. So I want to remind you that there is a supplement which addresses this question: when can we actually solve this mathematical problem? Please view that. And so now let's take a look at a geometrical interpretation of the mathematical problem that we just posed. Here on this graph, with the horizontal axis is the time axis, the independent variable, and the vertical axis is the dependent variable y, which we seek to solve. So solving the problem means finding the solution y as a function of time. This graph that y has as a function of time, that is what we are trying to solve. What do we know? We know that at t equal to t0, the initial slope of this curve is given by the value of f evaluated at y0 comma t0, and at any point during the evolution, the slope everywhere along this curve is given by this differential equation. So the differential equation tells us the slope at every point as a function of how the solution itself evolves, and the object is to find this overall behavior.